Today is Friday, the 20th of October. We're anxiously awaiting the debut of Tropical Storm Tammy, who is approaching the Leeward Islands, the lower Leeward Islands, and is going to visit us in the next 24 hours. Tammy will make her debut as a full-fledged hurricane within the next 24 hours, and she will afflict the outer Leeward Islands more so than us, but it's expected that we will experience tropical storm winds. Of course, the track of Tammy could change. So I want everyone to be aware that as Tammy moves north, if you pay attention to the rotation in counterclockwise fashion on the map, it's likely that the winds will afflict us first from the southwest, then from the south, then from the southeast as the storm approaches and passes to the east of us. It's a matter of geometry. In any case, I hope everyone gets a chance in the next few hours to prepare and to get situated, to be safe and to be dry, okay? So with that in mind, what I'd like to do is proceed with an item analysis of our Module 3 assessment first attempt. Now this was, and I want to highlight with everyone here, and this is where I walk into the room and I look into the camera, right? So this is for a fact. I'm going to say that one thing that I want to share with everyone here is that this is the toughest module. As far as understanding and being able to, on a first attempt, get everything right, this is the most difficult module of the entire course. And it's quite common for the initial attempt averages to run very low. However, once we review the mistakes and go back in, and then you make your final attempt of the module assessment, the odds are really good that the class average for this assessment increases or improves dramatically. So with that said, what we'd like to do is go ahead and begin our review of each of the items that pose the greatest challenge for our students. The first item that created the most difficulty for students was a multiple answer question. The multiple answer question required more than one correct response. And I'm going to put my smartphone on stun so that we don't get all sorts of stuff here, right? Okay. The multiple answer question reads, you are tasked with devising hardware controls based upon logic and probability. The first time you read that, you should say, oh, what part of the study guide did we talk about probability? Does anyone recall the example, the vivid example we used?
The slot machine.
The slot machine, yeah, probability, right? So you were told to increase the odds that a desired outcome, meaning true, when it's true and there's a 1 and the current is flowing, we have a winner, right? The odds that a desired outcome, winning the jackpot, will occur after a lower number of trials. Another criteria of the task is that you must begin your design with a component known to be more restrictive when it comes to true outcomes. It's the very diagram we shared. Did the diagram in our study guide for that segment begin with ors or ands? Does everyone understand what I'm asking here? Everybody know what I'm talking about?
Kind of. Didn't it begin with ands?
It began with ands, and ands are more restrictive, right? So if we zip all the way down to this, it begins with ands. Those are more restrictive. So that's one of our answer choices, right? That is one of our answer choices. The use of and logic gates first is best. That's because we want more restrictive outcomes. Choose the options below that will accomplish this purpose. Initial logic gates should be configured in parallel versus serial. This arrangement, the ands are in parallel. Here, if we break out the 4 input and, there are 3 ands in series. That's what we covered in class. So this has a greater chance of being true. This has a greatly reduced. This is 4 out of 4 times with a series of inputs. In this case, if we take 8 sets of inputs from A to H, only 2 out of 16 or 1 out of 8 will occur true randomly if it's completely random. Okay. So this is called intermittent reinforcement. When 1 in 8 pulls hits pay dirt, that's where the hook happens. If you feed, so B.F. Skinner was a world famous psychologist, and he did experiments with rats. And what he found out is that if the rat presses the lever to get fed, and the rat is fed every single time, the rat gets lazy and the rat doesn't press the lever very often. Because the rat knows every time I'm hungry, I'm just going to press the lever. But what happens if we change it so that the rat, this is operant conditioning, this is psychology, right? This is how addiction works. So if you hit 1 every 8 or 10 times, if the rat has to press the lever a bunch of times, this is a visual thing, right?
Yeah.
So now the rat is going like a banshee, going. This is what happens with gambling addicts. The payout only happens every so often, and the strongest form of conditioning behavior that reinforces that behavior is something called intermittent reinforcement. So there is some actual serious psychology behind this. Okay, that's why we spend quality time on it. Is there any, does anyone have any questions or comments at this point? Okay, use more logic gates for input interfaces, right? So in our diagram, we're using more logic gates for the input interfaces instead of 2 logic gates. We have 4 input, we have 4 logic gates for inputs. Here we have 2 logic gates for inputs. Does everybody understand what we're breaking out here on this item? Okay. So, any questions, comments about this one item? Everybody's going to do better the next time you see this, right? Next time you see it, it might be a different scenario. I might ask you, how do we decrease the chance, right? In which case you're looking at you're looking at this diagram as opposed to this diagram, right? The next question that posed a challenge for our students, which logic gate, so we have an input, and what's happening is that the inputs are being switched. Which logic gate in our class did we talk about where you can switch inputs? Anybody?
Inputs?
Yeah.
The multiplexer.
The multiplexer or MUX is correct. So some answered XNOR or DMUX, but in your study guide, it mentions that explicitly. Okay. Let me check one thing here real quick. Hello, Arvosan. How are you today?
I'm fine.
All right, so we're reviewing the item analysis for the deadline for the first attempt of the Module 3 assessment passed at 10 a.m. this morning, and now we're reviewing the answers. That's what we're doing.
Okay.
So another challenge that posed, another challenge for students was a true-false question that reads, a diagram shows an input order for logic gates to be C and A for the first logic gate, and B is an input for the last logic gate. The order these are listed in HDL for N does matter. It will not load and run correctly if the HDL order does not match the diagram. Is that true or false?
True.
It is true if the diagram shows an alternate sequence of inputs. Now, if the diagram is constructed generically, then it wouldn't. In other words, if you're sure that the logic gates are correct and how they operate is correct, then it doesn't matter the order that they're listed in the HDL. There are exceptions, and I want you to be aware that there are exceptions. For example, if you have a Boolean function with parentheses around that forces a different order, right? So I'm going to verify this and check on it again just to be sure. Are there any questions about this one item? So there are cases when custom differences make that complex logic gate work differently. All right, multiple choice. The implementation view of an important logic gate is shown below as logic gate 1. What type of logic gate is logic gate 1? Well, it's right there in your study guide. This is another version of the XOR, right? So there's two versions that we covered, and your author shows two versions, right? There's the version on top, and there's this way of doing it with NANDs and ANDs. If we take the not and the and the not and the and instead we use NANDs, and then we change the structure, we can do it with fewer logic gates. Still the same XOR. If you do it with more basic logic gates with a separate not and a separate and, you have to have a crisscross there. So that's the difference. Still behaves like an XOR. And at the end of the day, this is still the truth table. This right here is still the truth table for an XOR. XORs detect differences in the inputs. Okay, it's like a difference detector. Any questions about this? The next item that posed a challenge for our students was a multiple answer question. Students answered correctly less than half the time. It relates to the casino example again. You are tasked with devising hardware controls based upon logic and probability. You are told to decrease the odds that a desired outcome will occur after a lower number of trials. Another criteria of the task is that you must begin your design with a component known to be more restrictive when it comes to true. Choose the options below that will accomplish this purpose. The use of AND logic gates first is best. That's the same case. It's just the other case we talked about. Can everyone see the screen?
Yes.
So we're working with ANDs because that's more restrictive. The ANDs are connected in series, right? Let's go back to this. The initial logic gates should be configured in serial versus parallel. That means we have ANDs with more than one input, and they're stitched together in daisy chain fashion, serial fashion. And then we're using fewer logic gates for input interfaces. So we're only using 2 logic gates for input, as opposed to this case where we're using 4. We're using twice as many logic gates for the inputs. Does everybody understand what we're saying here now? Any questions?
No, sir.
Ordering. You were given the implementation of a diagram, the implementation version of a diagram for a compound component made of simple logic gates. Order the tasks you should follow to create the HDL and run the prototype in a hardware simulator in the most efficient manner. This is quite literally the steps that you follow in your solution. If you have not completed the solution yet, either in module 2 or in module 3, the steps would be unfamiliar to you. And this is something we want to review, right? So the first thing you're going to do based on the diagram is write out the Boolean function. Then you're going to do the truth table. Then with the truth table, you can list the canonicals. Then once you have the canonicals, you can do the logic. Does everybody understand that sequence? First the Boolean function, then the truth table, then the canonicals, then the logic statement. Now, sometimes you're given the canonicals. Sometimes you're given the logic statement, you have to work backwards. Or you're given the HDL. And so by the time we get to the end of the course, you'll have more practice doing that. But this is probably the hardest or most challenging time to work in this fashion. And as I said before, module 3, the initial scores are lower, right? So the average score was about a 52 in the class. So when you reconcile this, we'll post 2 points for reconciliation. Everybody? If you correct the mistakes on this and you reconcile, you'll earn twice as much credit. And then you'll be ready for the final attempt, okay? This is one reason why students didn't do as well. You had 60 minutes to do this bad boy, and of the students that attempted this thing, right, a majority of students attempted they logged their first attempt of the module assessment. They spent less than half the time they were allotted. So students are still rushing instead of taking time to look at the study guide and to check their notes and to reference things. Okay, so that's one reason why if you're rushing, that's a challenge. Let's continue. There was a multiple choice item that proved difficult. The selector input of a MUX digital component with 2 other input sources, input I0 or input 0, I sub 1 or I1, right, is receiving the following repeating binary values, 1 0 1 0 1 0. What will result from this selector input? Each value selects back and forth between the other source inputs, 0 and 1, 0 and 1, 0 and 1. Okay, so that's what's happening. That's the correct answer. We had other students that selected the other bogus answers. So when you're alternating 1 0 1 0 1 0, what you're saying is okay, we're flipping back and forth between I0 and I1. Any question about this item? Does everybody know what we're talking about in the study guide? In the MUX. Talk about the MUX. So this is the input 1 0 1 0 1 0 1 0, and it's flipping between this one, that one, this one, that one, this, and that one. Okay. That's what's going on there. All right, moving right along. You are told to create an OR logic gate using wires, a battery, some switches, and a light bulb. Select the statement below that is most accurate. The switches must be connected in parallel, that is arranged next to each other. Right? So on the first page of the study guide, it's this one. That's the OR circuit. Parallel means they're side by side instead of in series, one after another. Which Boolean operator is commonly represented by diagram K? This one. And the answer is XOR. If you see a logic statement, if you see an expression that has to do with Boolean logic and you see this operator, that's an XOR. And instead of a dot, which is AND, or a plus sign, which is OR, right? Everybody got me? Now, we did put out a revision to the study guide. Did everyone see the new revision for the study guide? And did everyone see the notice for the new revision of the study guide? Does everybody see module 3 study guide revision 1D? Right, so we put out a final version. We sent as the window to engage the module 1 assessment. Your first attempt went out. We said, hey, discard other older study guides. And one thing I want to call out to you is we enhanced some of the detail at the bottom when it came to this information. We included a view of what the XOR looks like in interface view, okay? Here's something else we did. We included information about how a NAND is represented in an equation. So if the crosshair symbol is XOR, the upward pointing arrow, it's called a Sheffer stroke, that's the symbol that's used to show NAND in an expression. That's additional, that's new information. So NAND is receiving two inputs, A and B. This is how the expression looks. When you're doing XOR, you're using this symbol. When you're doing AND, it's a brown black dot. When it's OR, it's a plus sign, right? Everybody knows what I'm saying, right? Okay, does anyone know? Right, so this is the XOR, and if you put a not in front of it, which is what this 0 represents, now we have an XNOR instead of an XOR. If you look at this, it's the same as this, except that there's a not right in the front. Does everyone know what the, so you can also see this caret symbol. Sometimes in expressions, they'll show the caret symbol that also represents this operator. So there's two ways that XOR can be represented in expressions. One is using the caret symbol and one is using the crosshairs. I call it the crosshairs. Any questions? Does anyone know what the symbol for XNOR is?
No, sir.
Well, actually, I'm sorry. Let me ask that question again. Here is the symbol for XNOR. Let's go back to this. Does anyone know what the operator symbol is for NOR? Have you ever noticed that I don't put everything in there?
The arrow pointing down.
Yeah, but I put links, don't I? Yeah, arrow pointing down might make sense. Yeah, might make sense, but NANDs and NORs behave kind of differently. So where could you find that information? Go here to this great website, or you could let's take a moment to Google here real quick. Usually, okay, yeah, actually for NOR, yeah, you're right. For NAND, it's an upward pointing arrow. The Sheffer stroke, for the NOR, it's the downward pointing arrow. So actually, that's something we can include in the addendum. So what we may do is post an update to our addendum in the references. So we have a study guide with a new revision, and in the addendum, we'll put the symbol, the operator symbol for NOR in the addendum, just so that you have that information. So NAND and NOR, it's really important. And this is very helpful. So I'm going to call out this. NAND is always 1 unless all inputs are 1. And then you have a 0. So the output of a NAND is false if all the inputs are 1. A NOR is always 0 unless all inputs are 0. In which case it's represented by 1 standard canonical. So NAND is always 1 unless everything is 1 going in. NOR is always 0 unless everything that's going in is 0. So their functions are related. All right. Let's go back to our excuse me just a second. Have our item analysis back up in just a moment. And we're almost done. Ordering. Was it this one we were on? We went on that one already. Talked about the wire construction, compound logic gate of a diagram and the order, devising hardware controls based on logic and probability. We covered this, right? It was a reverse case. Which logic gate? Diagram H, that was the crosshairs. Okay, true, false. And was that? Yeah, actually that posed a challenge for some students as well. Let's take a look at that one. A diagram shows an input order for logic gates to be C and A for the first, this, and does matter. We already answered that question, so that's just a repeat of the other truth, okay? Just remember that if there are special accommodations to change the order of the inputs and the diagram of the input, or how the Boolean function is stated with extra parentheses, that changes the Boolean function, it changes the complex diagram. So when you're doing custom things to change the order, then the HDL statements do have to be different in order for that to render properly. Okay, 2 more and then we're done. So the implementation view of an important logic gate is shown below as logic gate 1. What type of logic gate is logic gate 1? XOR. Is that a repeat as well? Did we all?
You went over.
It seems like that's a repeat, right? Oh, you know what? I know why I'm getting different. I'm getting some of the same questions again. I didn't sort. My mistake. Okay, let me do this. There we go. My bad. So you were told to use logic gate combinations to implement a custom hardware solution. One of the design requirements is to ensure the behavior of the solution is true for most input scenarios, but also false for a significant number of scenarios. So we don't want it false most of the time, and we don't want it true most of the time, right? Choose the best options that will accomplish this goal using a minimum number of logic gates, okay? Use mostly OR logic gates and some AND logic gates. So you're gonna have some trues, but then the ands will trim that down. Does that make sense? So the ors are like, yeah, everything's true. And then when it passes the ors, it hits the ands, and the ands thin out some of that. If more of the inputs coming out of the ors are true, that means that the ands will be true more often. That's what we're saying. Devises serial arrangement of OR logic gates first. So what we want is to have the ORs in series instead of parallel. So we don't want the OR behavior to be maxed out. We don't want everything to be like massively OR. We want the first behavior to be OR so that most of the ones are produced, and then we want to trim them down a little bit. I don't know if I'm making sense, but are there any comments, questions, observations? Okay. Oh, no, we just went to that one. A demux. Select the statement below that best describes the function of a demux compound logic gate. It uses select inputs to switch between multiple outputs. So a mux will switch between inputs. A demux will use signaling to select outputs. Okay, does that make sense? That should be explicitly stated in the study guide. It has been said that an XNOR with many inputs is ideally suited to detect what? If all the inputs are the same. So if all the inputs are false, or all the inputs are ones, and you have lots and lots of inputs, an XNOR is going to say, oh, they're all zero, oh, they're all true. That's what XNOR is really good at doing. That's the behavior. XOR will detect if any of the inputs are different. And it'll show zero if all of the things are true, okay? Last question. In the list below, match the output and canonical type with the logic gate that produces such results. That gets back to the screen we were just showing you. In our there was another reference, and it was a summary of everybody knows what I'm talking about, right? Mm-hmm. It's in here under references, and it is this canonical summary. How you answer that last question, all you do is reference this. This is the summary of canonical behaviors. So when you're answering that last question, everything you need to know is right here, so you can match each of those behaviors. Let's take a quick look at that just to make sure everybody's on the same page that way. Now, one thing I'm going to do as soon as we finish here, I'm going to post the reconciliation, 3.4 reconciliation, so that you can complete the reconciliation. Again, it'll be worth twice as many points, okay? Whoop. Zero unless all inputs are one. Standard canonical, AB, that's the AND. Zero unless all inputs are zero. The standard canonical is So it's true when A is ticked and B is ticked. That's a norm. 0 unless all inputs match. It's a standard canonical and it's true when they match all 0 or all true. That's an X norm. We just went over that, right? 1 unless all inputs match, reverse AB and A tick B tick. So that's the XOR. It's detecting when things are different. And when things are all the same, it produces a false. All right. If you memorize the summary of canonical behaviors, that one sheet, you'll get this. Okay. 1 unless all inputs are 0, and it's the reverse canonical A tick B tick. So the output is 0. It's 1 all the time, unless all the inputs are false. That's an OR. And then 1 unless all inputs are 1. That's a NAND. So if we put all the inputs in as true, it'll reverse. It'll produce a 0. It'll be false. Okay. Any questions about our assessment items? Okay, that's it for today. I'll go ahead and post the reconciliation here. 2.4. I'll post 3.4 here. Please reconcile your assessment. And we'll see you Monday. Please stay safe and dry. Okay. Thank you for joining us. That's it for today.